assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we have a conductive triangular wire loop here that is free to rotate about this axis right here. And it's sitting in a plane where on the left side of our XY plane here, there's a constant uniform magnetic field, and on the right-hand side there is none. And so as this thing rotates around, the flux is going to change through the loop in time. And because of that, there's going to be induced currents in this loop from Faraday's law for induction, right? And what we want to figure out is by using Lenz's law, we want to determine what the direction of those induced currents should be. So we're going to do this for a few different spots as it crosses the y-axis, minus x-axis, minus y-axis, and plus x-axis. Okay, so for the plus y-axis, we can see that as our loop enters in here, it's going to be increasing in magnetic flux because it starts with none and then it's going to have some, right? So we know there is an increase in flux. And we know that the magnetic field is going to be into the page. Now remember, if there's an increase in flux, what we want to do is we want to induce a current that will oppose that increase, which is going to be the opposite of whatever the direction of our original field is. So to do that, we'll want a magnetic field that is out of the page, so pointing towards us. And if you point your thumb out of the page, we can see that our fingers should point in a clockwise direction, or sorry, a counterclockwise direction if we turn it around. So for this one, we should have a counterclockwise current. And again, that's because, I should say, we want AB out of the page. Okay. So for each of these, I will say which direction we want the magnetic field from the induced current to be and how that makes us choose the direction of the current. Okay, so for part two, it's going to be as we're crossing the minus x-axis here. So you can imagine if our triangle is crossing the minus x-axis here, it's going to be sitting in a uniform constant magnetic field the whole time, and the flux really won't be changing because even if it's moving around from spot to spot on the left side of our plane here, the number of field lines going through it is going to be about the same. So the flux isn't going to change because the area doesn't change and the field doesn't change. So we can just say there's no induced currents. And if there's no induced currents, we can't really talk about the direction of the currents. Okay. For part three, we'll be looking at the minus y-axis. And for this one, we can see we're going to be going from a region where we have a magnetic flux to where we have no magnetic flux. So our flux should be going down as we cross the minus y-axis. So flux is going down. And the direction of our field during that time is into the page. So remember, if the flux is going down, we'll want to create a field that is going in the same direction as the existing field. So we will want to have an induced current to make a magnetic field that points into the page as well, to try to resist this decrease. So the direction of a current that will produce a magnetic field into the page, let's use the right-hand rule to figure that out. So point your thumb into the page, twist your hand, and you should see that your fingers loop around in a clockwise direction. And that makes sense, right? Because we expected this answer to be the opposite of the answer for number 1, because it was a very similar situation, except now we had decreasing flux instead of increasing flux. So it should be exactly opposite. Okay. So now, finally, let's look at the plus x-axis. And over here, we can see that if we're crossing plus x, our triangle is just going through a region where there is no magnetic field, therefore there is no magnetic flux, therefore no change in magnetic flux, so we can't have any induced currents. So it's always important to remember that we only get those induced currents when the magnetic flux changes, right? That's Faraday's law of induction. All right, so there you have it. We determined the direction of all our induced currents as our triangular loop here crosses each of the axes in this diagram.